Suppose z is equal to f of xy is the objective function we have, and gxy be the constraint on this objective function. Now, on taking differentials, how can you write this? You can write this dz equals to fx dx plus fy dy. This is what you can write. For the constraint, what you can write, gx dx plus gy dy equal to 0. Now, you can write this as gx dx is equal to minus gy dy, or you can write this as dy equals to minus gx dx, sorry, gx upon gy dx. This is what you can have. Now you can substitute this dy here, so what you will get is dz, which is equal to fx dx plus fy into minus gx by gy dx. So you have everything now in terms of dz and dx. So in case if I want to write this as dz by dx, this will be fx dx by dx plus fy minus gx by gy dx by dx. So you can write this as dz by dx fx minus fy gx by gy. This is what you will have. Now for maxima or minima, in case if you want to optimize this, then dz by dx have to be equal to 0. Well, this would imply that even the RHS of this has to be equal to 0, which means fx minus gx by gy fy should be equal to 0, which would imply that fx is equal to gx by gy fy, and which would imply fx by fy equals to gx by gy. Now this is one of the condition for the optimal. Now let us talk about the Lagrange multiplier method. So what we have done is that this is one of the condition which we have got. Now we also have the constraint which is gxy. So this condition along with gxy equal to 0 can be used to find out the critical points of this f function. Now this is the first order condition. Okay, you have to remember this. This is the first order condition, and this along with the constraint gxy equal to 0 can actually fetch you the critical points. Now point is that let's talk about the Lagrange multiplier method. Well, supposedly if you have the function fxy, this is the objective function which you want to maximize or minimize, and you have the constraint gxy equal to 0. This is the constraint which you have. So you can form the Lagrange function as script L, which is you maximize, or this is your objective function subject to this constraint gxy, where this lambda is Lagrange multiplier. Okay, this lambda is Lagrange multiplier, and you have to understand one thing, that gxy is equal to 0. This is the constraint which you have. Okay, in case if this is equal to 0, then the value of this L, okay, is going to be equal as the value of this Z, which is equal to f of xy, because this is equal to 0, so the value of L is going to be equal to the value of Z. So if you maximize this Z or you maximize this L, you're going to get the same thing. Okay, so you're going to get the same thing. Are you understanding the point? So let us try to maximize this L. So what you do is that what you will try to do is that you will find out 3 partial derivatives, one for each variable and one for the constraint. So you have del L by del X as fx plus lambda gx equals to 0. This is what you have. Del L by del lambda is fy plus lambda gy equals to 0. And del L by del lambda is gxy. This has to be equal to 0. So in case if these are 3 conditions that you have, 1, 2 and 3, so you will simultaneously solve each of them, and supposedly in case if you solve this one, the first and second, so what you will get is fx equals to minus lambda gx. Okay, and here you will be getting fy equals to minus lambda gy. This is what you will get from the first and second equation. So dividing first by second, what you will get is fx by fy is equal to gx by gy. This is what you're going to get. And remember this, that this is same as you have got above here. This is same as you have got above here, where we haven't used any Lagrange multiplier. So, and remember this, that the critical point which is going to be obtained, okay, it will satisfy. So supposedly you get some point x star y star at which this is going to be holding, this condition is going to hold. Now this this critical point will also satisfy gxy. So if you substitute these x star y star into gxy, gx star y star will also be equal to 0. Okay, so